Chapter 4, Introduction to Probability. In this video, we'll be focusing on the rules of probability, and I'll do a separate video for Bayes' theorem. Here are the rules of probability. We'll be covering each one, including some examples to explain how they work. So the first probability rule, the probability of something happening is always going to be between 0 and 1, where 0 has no chance of happening and 1 is a 100% chance of occurring. Probability rule number 2 states that when we add up all the probabilities of all possible outcomes, it should equal to 1. Let's see how probability rules 1 and 2 go together. Say a sales manager has placed 3 products on display in a Target store. The following shows the probabilities associated with the number of these products that sell in the first 30 minutes on display. So here in our table, on the left, we have X representing the number of items sold, and then P of X is the probability of that many items being sold. So for instance, there is a 0.2 probability that 0 items will be sold. So here's rule number 1, in that for any event of interest, our probability of it occurring will be somewhere between 0 and 1. So you can see each of our probabilities here are between 0 and 1. According to rule number 2, if we add up all our probabilities, all our possible outcomes, it should equal to 1. Let's look at rule number 3. In this rule, the probability of an event of interest is equal to the sum of the probabilities for each individual outcome forming that event of interest. So for instance, if what we're interested in has 3 potential outcomes to occur, the probability of each one will be added up together. Let's look at the example. Same story as before with the sales manager in Target. And here we've got the probabilities for the number of products that sell in the first 30 minutes on display. So if we wanted to know what the probability that 2 or more products will sell, we would identify our related probabilities and the particular events we're interested in this case, 2 or more products. With our event of interest being 2 items sold or 3 items sold, we then would add up the probability at each event to get our total probability of our event of interest. In this case, 2 or more products will sell at 0.5 probability or 50% chance. The complement rule states that the probability of the complement of an event E is simply 1 minus the probability of that event. And this is related to rules 1 and 2. So again, using our same Target store example, we have the probability shown here. And we now want to know what is the probability that 1 or more products will sell. According to our previous rule, we can simply add up the probabilities for 1 or more products. In this case, 1 product is sold, 2 or 3. When we see that, we'll be adding 0.3, 0.4, and 0.1 for a probability of 0.8 that 1 or more products will sell. Using the complement rule, we can find the same answer in a faster, simpler way. We would look at the complement of what we're interested in. In this case, the complement of 1 or more is what's left, in this case, 0. So what we can do is then take 1 minus our complement, in this case, the probability of 0 items being sold is 0.2, and we get the same answer. Our probability rule number 4 is an addition rule for any 2 events. Here, when we talk about 2 events occurring, you'll see the word or, which means we add. So for instance here, if you've seen a Venn diagram before where 2 areas overlap in the middle, where they occur jointly, we can see here in our example, if we took a pack of 52 cards and we wanted to see the probability of drawing hearts or drawing kings, we will notice that there's an overlap, that there is a king of hearts as well. So the formula states that we'll take the probability of event 1, in this case, cards with hearts, plus the probability of our second event, cards with kings, and then subtract the probability of getting a king with a heart. And the reason why we do this is because we do not want to double count the probability of our king of hearts appearing, because we see that there's an overlap here. Let's look at another example of the same rule. Say we're drawing from a deck of 52 cards, and we want to know what the probability of drawing a red card or an ace. The or tells us that we're going to use the addition rule because we want to add up the probabilities of getting either a red or an ace. So first, we'll have to look at each probability occurring. We know that there are 26 red cards in a deck of cards. So there's a 26 out of 52 chance that we get a red card. In that same deck, we know that there are 4 aces. So we have a 4 out of 52 chance of drawing aces. Notice though that what we have identified as our probabilities for red cards and aces has an overlap of red aces specifically. So we will subtract 2 over 52 because we don't want to count the red aces twice. And so we've got a fraction here where we'll add up 26 and 4 and subtract 2 with the denominator over 52. And that'll give us our probability that we either get a red card or an ace at 0.54. As you can see in the chart here, we're doing a joint frequency table, which we learned about in Chapter 2. For the probability rule number 5, again, this is another addition rule, but this is specifically for mutually exclusive events. So there is no overlap. And so for instance, here we have aces and kings, and there's no overlap between the two events. So to find the probability of pulling aces or kings, we would simply add the probability of each together. Let's look at an example of rule number 5. Boot World has 3 styles of work boots, 6 pairs of style A, 12 pairs of style B, and 2 pairs of style C. If a store clerk randomly picks 1 pair to put on display, what's the probability that this boot will be style A or style C? So again, the or tells us that we're going to add up both probabilities. So here we would identify the probability of each boot occurring. We know that there are 6 out of all 20 boots, so there's a 0.3 chance that that'll get drawn. We know that there are 12 pairs out of the total 20. That's 0.6 chance of getting a style B boot. And for style C, there are 2 pairs possible out of all 20 boots. That gives us 0.1. Because if one boot style is selected, another style cannot be selected because the store clerk can only pick 1 pair. We know then that the events are mutually exclusive. We know boot A is 0.3 chance of occurring, whereas C has 0.1 chance of occurring. So we'll add up those probabilities, and it gives us a 0.4 chance of pulling either style A or style C. Now, even though I'm talking in decimals, we can always convert this into percents. So 0.4 is the same as saying 40% chance of pulling style A or style C. Now, the conditional probability states that the probability of one event will occur given some other event has already happened. That means there's a connection between 2 particular events occurring. So it's written here where we have event 1 given event 2 occurring. And you'll notice that at the top, we've got the probability of both events occurring together. That's the joint probability. And then we divide it by the probability of our second event. That's known as the marginal probability. So let's look at an example. Here we have the managers of a golf course who conducted a study on the types of golf balls that golfers use based on handicap. We've got a joint frequency table for 100 golfers surveyed. If a player has a handicap of 10 or more, what's the probability that she will use a Nike golf ball? So here is our table. On the left here is the handicap, and up top here is the type of golf ball or the brand. Note that I've identified each event of interest here so that you can see specifically what we're looking at. For instance, we want to know where the event of interest, E3, is someone that has a handicap of 10 or more. So we're looking at this row here. And at the same time, we're looking at the probability under event 6 where someone's using a golf ball. So I'm looking down at this column here. So sometimes it's helpful to mark the event of interest along the rows and columns to help organize your thinking. So our 2 events of interest are players with a handicap of 10 or more and those that use a Nike golf ball. So our probability statement of interest states that what's the probability of someone picking a Nike golf ball given that they have a handicap of 10 or more? Using our probability rule, we'll take the probability of our choosing a Nike golf ball and having a handicap of 10 or more. So what you'll want to do is read the joint table, finding our handicap of 10 or more, and going across until you get to the Nike column. So we're looking for people who are both Nike users with a handicap of 10 or more. That's where we'll put the 10 on top of our numerator. And then we want to divide by the probability of our event 3. In this case, people with a handicap of 10 or more. So if I look at my row here for event 3, I can see the number of people who have a handicap of 10 or more. So I'm going to add up all the numbers in this row. So I'll add 7, 8, 10, and 23. That gives me 10 over 48. So the probability that someone will choose a Nike golf ball, given that they have a handicap of 10 or more, is 0.21. So probability rule number 7 is the conditional probability for independent events. So recall, independent events do not affect each other in any way. And so the conditional probability of one event occurring, given that a second independent event has already occurred, is simply the probability of the first event occurring. So the multiplication rule is our probability rule number 8, and it can be used whenever we want to find the probability of two events, but we do not know the joint relative frequencies. So let's look at an example. It's a bit more straightforward. So imagine we have a small boutique hotel which has 20 rooms. 5 of the rooms are suites with a living room and a bedroom, while the other 15 are traditional hotel rooms, meaning they don't have living rooms. What's the probability that the first 2 rooms booked during the week of October 13 through 19 are both suites if the bookings are assumed to be random? So we use S to represent suite and T to represent traditional. In this case, though, we only care about the suites themselves, and we want to find the probability that our 2 rooms that are booked will be suites. So you can see here, what we do with our formula is that first, we take the probability of getting a suite. So since we know that there are 5 suites out of 20 possible rooms, we take 5, divide by 20. That gives us the probability of our first room. Now, because we want to know about 2 rooms, we have to multiply it for the second event, which is the second booking. We now change our numbers. Because the first room is already booked, we have to take it out of our possible outcomes. So in this case, now that we have 1 suite already booked, that leaves me with 4 suites still available to be booked. And since we've already booked 1 room, that leaves me with 19 rooms remaining. So my second event is 4 suites remaining out of the 19 remaining rooms available in the hotel. When we multiply our fractions across, we get the probability that our first 2 rooms booked in October will be suites at 0.053, or 5.3%. Multiplication rule for independent events is probability rule number 9. When our events are independent, we simply multiply them together. So here we have a Midwestern city with 3 major airlines that serve the airport. Suppose 60% of passengers fly United Airlines, 30% fly Delta, and 10% fly Southwest. Further, suppose that 70% of the flyers are flying for pleasure and 30% fly for business. Assuming that the type of trip and the airline used are independent of each other, what's the probability that a flyer uses United and is a business traveler? We'll take the probability of a United flyer and the probability of a business traveler, multiply them to get a 0.18 chance of a United traveler traveling on business. Let's practice some of these rules of probability. So the URS Corporation Construction Company has submitted 2 bids, one to build a large hotel in London and one to build a commercial office in New York City. The company believes it has a 40% chance of winning the hotel bid and a 25% chance of winning the office building bid. The company also believes that winning the hotel bid is independent of winning the office building bid. So first, we want to set up the probability of winning the hotel bid. So we know that's 40%, so I have my probability right here. And the probability of winning the office building bid is 25%, or 0.25. The probability that the company will win both contracts is our multiplication rule of independent events, where I'll take 0.4 times 0.25, which gives me 0.10 chance of winning both bids. Let's look at what is the probability that URS will win at least one contract. So in this instance, we would take the probability of winning the hotel plus the probability of winning the office building and subtracting the probability of winning both contracts. And that gives us a probability of 0.55 of winning at least one contract. Let's say we also want to know what's the probability that URS will lose both contracts. Since we know the probabilities of winning the contract, we can use the complement rule to know the chance of losing. So for the probability of losing the hotel, we would take 1 minus our probability of winning. So 1 minus 0.4 gives us a 0.6 chance of losing our hotel bid. And if we do the same thing for our office building, we'll take 1 minus the chance of winning, or 1 minus 0.25, and that gives us a 0.75 chance of losing the office bid. And since we want to know the probability of losing both contracts, we'll use the multiplication rule of independent events and multiply our probabilities of losing each contract. And that gives us 0.45 chance of losing both contracts.